Problem 19.9. We're told that a proton is moving at 4 times 10 to the 6 meters per second through a magnetic field of magnitude magnetic field of magnitude 1.7 Tesla. It experiences a magnetic force of 8.2 times 10 to the negative 13 newtons. And then we're asked to find the angle between the velocity and the field, the magnetic field, right? So, well, we have a formula that we can use. That formula is charge times velocity times magnetic field, both of magnitudes, sine of the angle. So all we're doing is a little bit of algebra to solve for the angle. It's pretty straightforward. We're told pretty much all of, I had to add this because this is a vector. So we're told all of the information, right? We're told FB, which is the magnetic force, this thing. We're told the charge, we're told the velocity, and we're told the magnitude of the B field. So now let's take these three things to the other side. QVB equals sine theta. And then we just take the arc sine, take the sine inverse QVB, and that's going to give us, well, let's write everything out again so we know what we're doing. 8.2 times 10 to the negative 13 newtons. Over, what was it? 1.6 times 10 to the negative 19 coulombs times 4 times 10 to the 6, 4 times 10 to the 6 meters per second times, what am I looking? 1.7 Tesla. So these are all in standard SI units, so we should be good. And this is going to give us a value of 48.91 degrees. So all I did was rearrange. Took these to the other side, took the arc sine of all of that stuff on the other side. It gives you the angle. So that's the angle that you get, but that they don't specify where the horizontal is. So it could be 48.91 degrees, or it could be 131 degrees, about, depending on where your horizontal is. Okay, next problem. We're told that we have the Earth, and near the equator, this is the equator, we have a magnetic field of 50 microtesla. We have an electric field that's 100 newtons per coulomb, and it's pointing straight down into the ground, so straight downwards. I wrote it as negative r hat because I'm considering the, let's see if I have something here. I'm considering the radius of the Earth, right? So it's r hat, so r and r hat is what I'm saying. So E is the negative r hat direction. B field is in northward direction. So these are perpendicular. These are directly perpendicular. And then we're told the velocity, all right, we have one electron. The velocity of an electron is moving at 6 times 10 to the 6 meters per second directly eastward, right? So north, east, and then straight down. So we have north, east, and then straight down, which I'm calling r hat. Right, so those are all perpendicular, directly perpendicular to each other. So that'll make things a little easier. We are asked to find the gravitational, the electric, and the magnetic forces on the electron. Okay, so, well, first thing it asks for is gravitational force, which from, this is mass of the Earth, from the last course, last semester, you might remember this. r squared, but this is really just equal to gravitational acceleration times the mass of the electron, right? So that's the mass of the Earth, that's the mass of the electron, and this would actually be pointing downwards, right? So it'd be a negative force. And we'll just do it this way. So it's going to be pointing straight down, right? That's pretty obvious, I think. Okay, and then the next one is the electric force. The electric force, and this is, recall, the charge times the electric field. Well, we're told that the electric field is 100 newtons per coulomb, directed directly downwards, and the charge is 1.6 times 10 to the negative 19 coulombs, negative, because we're talking about an electron. So then, we have the charge times, let's just write this out, charge times the E field is going to be pointing negative times negative directly upwards. So that's going to be pointing straight out, away from the Earth. So that's the electric force. So it's actually pushing upwards, which is pretty interesting. And then the next one we're asked to find is the magnetic force. Well, the magnetic force, as we know, looks like this. Let me just, and let's look at this again. So we have the B field is directly north, and the velocity is directly east. So if we take V cross B, so let's point our fingers of the right hand along the direction of V, curl them towards B, we should have what we would expect to see is a magnetic force pointing straight upwards, similar to the electric force. But let's be careful because we have an electron, and that's a negative charge. So that's 1.6 e to the negative 19 coulombs times velocity, which is 6 times 10 to the 6 meters per second, times the B field, which is 50 micro. So it's micro is negative 6 Tesla. And sine of the angle is 90 degrees. That's going to be 1. Okay, so if we plug all of this in, we end up with, just double checking my work, we end up with 4.8 times 10 to the negative 17 newtons. And remember, we have this negative sign out here, so that's going to be in the negative r hat direction. So surprisingly, then, well, not all that surprisingly, but I mean, because we use the right-hand rule this way and this way to figure out where it's going to be, we thought it would be that direction. But it turns out it's actually pointing directly downwards into the Earth, right? So it's in the opposite direction of the electric force. So there you go. We have three forces. Gravitational force is pushing downwards into the Earth. The electric force is pushing upwards out of the Earth, and the magnetic force is pushing downwards into the Earth.